Welcome to this video. This is the continuation of moments using diverse methods, and this is the part two. So, this same question we are doing the principle of transmissibility now. So now this principle of transmissibility, we are just transmitting this force, this 600 Newton force, backward and forward along its line of action. So when you take it upwards, you know that before here you have a distance of 4 meter here, 4 meter, and from here to here you have a distance of 2 meter. So but now when you shift this from force back to this place, you will discover that the distance have already increased from here to here, and you know this one is f1, f2. In that way, you have eliminated f2 because f2 now is now part of this new distance. So let's call this distance d1. Should I call it d1? Okay, let's call it distance d1. So when we move this force along this line of action, it has eliminated f2. So we are now calculating d1 as f2 has joined with d1. So we are going to get this by adding 4 and this little distance here. How do we get this? We are going to use a kind of trigonometry here to get this f2. So before that, let me indicate our second distance. Our second distance will be at this axis, and we indicate this one as d2. So here, when we are done with this part, we move this force to the along this line of action again to this side. You know, this one was to the opposite place, so we are moving down here. So whatever we use here, whatever trigonometric function we use here, is the inverse that we are going to use here to get our distance. So the distance already eliminates, since this one is f1, this one is f2. It eliminated f2 here and join it to the distance. Here is going to eliminate f1 here and join and make the distance alone here. You understand? So now let's start. So we're going to, before we get our moments, we already have our f1 before. So we just need our d1 to get our moments 1. So let's get the d1. D1 will be 4 because here to here is 4, and we need from here to here. So this 4 plus here will be what? This is where we have to be very careful. So now this place is also equals to this place. So when you draw like a line from here to here, you see that it's forming a triangle already. So let's bring this one out. You have something like this. So here you have 2 meter, you have 2 meter here. So here is our f2, right? Here, see our f2 here. Then this angle, remember, is an angle of 40. So put this 40 here. So we are having opposite and we are having adjacent. So and which trigonometric function is that? That is tan. Tan is equals to opposite over adjacent. So what are we saying now is that tan 40 will be equals to opposite, which is f2, over adjacent, which is 2 meter. So you'll be having tan 40 is equals to f2 over 2. So we are looking for f2. You know, it's f2 that I want to join to d1 here to complete our d1. So you have f2 is equals to 2 tan 40. So that's our d1. So and that's the second part of our d1. So plus 2 tan 40. So what will be our d1? Let's calculate that. 5.678. We have 5.68 meter for this d1. So now we can calculate our moments about O. D1, your d1 will be 5.78. Then from there you can calculate your moments. Your moment as m1 is equals to f1 multiplied by d1. And what is f1? Our f1 is 459.6 multiplied by 5.678. So you have 2609 0.6, which is approximately what 2610 Newton per meter. So that is for M1. So now we are now dealing with what the second one, when you move the force along the line of action to the others to the point. Let's call this point B. Let's call this point C. So along to point C now, you are calculating for the distance D2. What's the distance here before? Is 2 meter here. So 2 plus, this time around we are using this and this in relation. So you are going to be having 4 cot the angle that is here, 4 cot 40. Since we use tan here, when you are coming here to come and use the opposite direction, you are going to be using cot. Remember, cot is equals to 1 over tan. So we are using the opposite. So without wasting our time, then we just have 4 cot 40, and that will give us, we have 6.767. 6.7, let me say 6.7, okay, 6.767. So now you can use your your second moment, which is going to be F2 multiplied by D2, and will be what was our second force, which is 385.7 multiplied by this 6.767 is going to give us, let's calculate that. We are also getting 2610.0 Newton per meter. So as you can see, for the principle of transmissibility, we are getting the same moment both on the moment 1 and on the moment 2. That is when you shift the force along its line of action to point B, and when you shift at the line of action to point C. So now let's just go to the last one, the vector. So the last one, vector notation. This one is very simple. You just bring out the component of the forces and resolve them, then indicate the distance from the as it is in the equation before. So we've done something like that before. So it's 18. So we know that there's 40 degrees here. So when you are resolving to the horizontal and you have the angle inclined to the horizontal, you already know that it's going to be the force cos the angle. Then here will be the force sine the angle. We've done the first part. So, and you know that this is y-axis, this is x-axis, and when you are dealing with vectors in this form, for y you have what, j. So this is going to be in j, then this one is going to be in I. What is the distance here? Distance here is 2 meter. Distance here is 4 meter. So what are we doing? We are multiplying the force that we have resolved into components and the distance. We are multiplying, we are crossing them together because it's going to lead us to matrix. So we are crossing, let us say we are crossing them. We are crossing them together. So let's move from there and let's write our moment out. So what do we have? The moment, we have the moment of, no, you have to calculate the moment. So you are having the position vector of OA, you know this is O and this is probably A. No, this is from the base. So multiplied by the force. The force that we now we have resolved, we have already resolved the force into what? This and this. So when we are writing the force, it will be in these two forms. When we are writing the position vector, so it will also be in these two forms. So let us move on that way. So here we have, this is going to be what, 2i plus what, 4g, because from here to here, if you are going to arrange it normally, it's going to be 4g then plus 2i, but you are arranging it accordingly now. So here we have cross, what's our first to the horizontal, you have 600 cos 40. So 600 cos 40i and plus this 600 sine 40j. So now that we have the two and forces, I think we can use our determinant form to move on from here. So you just bring out the determinant and you write your I and J because you're having only I and J. So for I here we have 2, for J here we have 4. Then for I here we have 600 cos 40. For J here we have 600 sin 40. So here now we use the normal determinant. This multiplied by this minus this multiplied by this. I think that's all you just have to do there. So but before that we can just resolve this for clearer information so that we don't mix things up. So let us resolve this. 600 cos 40 will give us what? Calculating the moment. Calculating the moment. So it's going to be this multiplied by this and minus this multiplied by this. Do we get? So from here you're going to be having 2 into brackets. This force here, I think this one is moving. We omitted something here. This force is moving downwards. You have to be very, very careful. So there's a minus sign here. For a force moving upwards, it's going to be positive. For a force moving downwards, it's going to be negative. So we should know that there's a negative sign here. So when we are doing this, we should put the minus here too. So that's how it's going to be here. So it means that here will be minus automatically. Why? Because minus times minus will be minus here. So here it will affect this. So which will be minus 385.7 then minus 4 into brackets 459.6. I have minus 771.4. Then we have minus 1838.4. So what do we have here? We are having minus 2609.8, which is approximately minus 2610. But note that this is just the moment. We are asked to calculate the magnitude of the moment. So when you are calculating for the magnitude, what are we doing? Magnitude of this will be square root of this, then the square root of this 2610, then square. You know we are dealing with, that's the formula when you want to calculate magnitude. It will be the square root of the answer then raised to power 2. So when you will have done this 2 times, you know that square root will cancel square root and it will also affect the minus 2. So it is going to be 26110 Newton per meter. So that is our final answer. Thank you very much. Like, share, comment, subscribe, and we are going to be doing more videos on applied mechanics. Thank you.